All right, time to get started. So here's where we were last time. We were talking about surface independence. Remember, it's sort of a rip-off of the idea of path independence. In fact, a shockingly analogous rip-off of the idea of path independence. It's like, oh my gosh, somebody took the same idea and then just kind of, translated a little bit. And you'll notice, of course, that everything in surface independence is one dimension higher than its counterpart in path independence. And you can see that on the diagram, right? So we've talked about this diagram previously, and we've talked about this part of the diagram, this little pattern, right? We have these special path independent vector fields, special fields. And, we can call them path independent, but we can also call them gradients. And we can also call them irrotational. Namely, all of these vector fields, regularity assumed, right? Very important. We do have to worry about singularities and differentiability issues, and that throws massive wrenches into all the work, so we're going to ignore most of that most of the time. But regularity issues aside, any vector field that has one of these properties has the other two, and vice versa. So path independence looks like this, and as I noted last time, surface independence, here's how strong the analogy is, right? The little diagram chase describing exactly what surface independence looks like is exactly the same pattern, right? Shocking. Almost makes it look like this diagram's natural. You know what I mean? Again, and it is in some very powerful ways. But Punchline is a really useful tool for y'all. Okay. So let's see. While we're here, I'll go ahead and remind you as well, this pattern. Right? Really useful pattern to notice. Now where I've got it drawn here, I'm just sort of recognizing what the diagram chase looks like for, on this diagram as drawn here, for Gauss's divergence theorem, right? And as we observed previously, if you were to do the same thing for the fundamental theorem of line integrals, it looks like that, same pattern. If you do it for Stokes' theorem, same pattern. Again, shockingly consistent, and very interesting that it is so consistent. Okay. All right, so anyway, back up here. So, and one other thing I was going to say in relation to the diagram, let's get rid of this. Remember, not only do the properties follow this analogy, but also you can use the diagram to speculate fairly accurately and reliably on what tools you can use to make what connections. And so, for example, how did we make the connection between gradients and path independence? Well, we used the fundamental theorem of line integrals. And you can go back to chapter 6 and remind yourself, when we first introduced path independence, I made the observation that gradients are all path independent, and you'll notice that fundamental theorem of line integrals was the key tool that allowed us to draw that conclusion. So, with that in mind, we might reasonably speculate that Stokes' curl theorem might be the thing that will allow us to connect being a curl with being surface independent. So let's test that theory. Let's see if that works. If I want to check that something's if I have a curl and I want to check that it's surface independent, does Stokes' theorem help us? And 100% totally does. So here we go. Here we have a curl vector field. Here we go. Curl vector field. We're going to consider two surface integrals. We're going to consider this green surface integral through, let's say that green surface. And then we're going to consider this blue surface integral through this blue surface. Orientations, blah, 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 like we discussed last time. You've got to be very careful to make sure that these do indeed have the same boundary. Right? Got to have the same boundary curve. Orientations and all. So, does this work? Is the green integral necessarily equal to the blue integral? Well, here's the thing. This green integral, you're going to notice, is a flux of a curl. By assumption, the orange vector field is a curl. Flux of a curl is exactly what Stokes' theorem, in fact, does address. And Stokes' theorem, therefore, in this case, allows us to rewrite that green integral as the boundary circulation there of the anticurl. And then likewise, let's look at the blue integral. Wait a minute, that too is a flux of a curl. That's exactly what Stokes' theorem addresses. And so it too is a circulation of the anticurl. And so, yeah, sure enough, green does equal to blue because they're both equal to the same boundary circulation of the anticurl, and therefore we have surface independence. And so as the diagram predicted, right, this is what I think is really one of the big takeaways here, and why I'm showing you this argument, is to show you that the diagram predicted that this is how the argument would go down. Right? And so that, again, means this is a really natural diagram. This is a really wonderfully natural and organized and beneficial way to organize these ideas in your mind. Right? So strongly encourage, try to think about, when you sort of organize these ideas in your mind, let this be the organizing principle right here, this diagram. Okay, now likewise, how did we make the connection between, let me go back, hang on. How did we make the connection between being a curl and being path independent? Oh, excuse me, sorry, I said that wrong. How did we make the connection between curl being 0 and being path independent? And now we did that fairly recently, actually. Stokes' curl theorem ended up being the tool. And so with that in mind, again, we speculate. This doesn't prove anything, but it sure seems to be suggested by the diagram that if I want to show a relationship between divergence being 0 and surface independence, maybe Gauss's divergence theorem is going to be the tool. So again, the diagram is helping us. The diagram is telling us what to try, what to think about. So let's see if it worked. Did the diagram lead us in the right direction here? And here's the argument. Now you're going to recognize the layout, right? And again, I always try to lay these things out. When arguments are analogous, I like to lay them out so that they look cosmetically analogous to emphasize the strength of the analogy and so to help you all notice the patterns, etc. So we've already discussed just now that being a curl is the same as being surface independent, and we previously discussed that surface independent means that closed boundary fluxes are 0. Notice this, just like the argument we made with path independence. And as predicted, we have this perfect little opportunity to bring up Gauss's divergence theorem because we have a closed boundary flux, and Gauss's theorem tells us that those are triple integral of divergence, and it's all downhill from here. We have apparently, check it out, this thing called divergence, all of its triple integrals are 0 everywhere, no matter what domain, any domain, all domains. Triple integrals always 0. How could that possibly be? There's only one way that these integrals could all be 0, and that is if the divergence itself is 0. And so, boom, just as predicted, right? The divergence theorem is the connection that allows us to see that divergence equaling 0 is our local test for surface independence. Again, just as the diagram predicted. So I think this is super useful, just crazy useful, and we're going to say a couple more quickie things about it. Sorry, I am going to do an example of surface independence, and then after that, I'll say a couple more quickie things, and we'll get to more examples. Today is going to be a big examples day. Okay, so just as a summary of what we just said, if you are trying to decide if a vector field is surface independent. Said differently, regularity issues aside, if you're trying to decide if something is a curl of something else, most of the time, to be honest, you're going to be more interested in whether it's surface independent. And the answer, and how you tell, is compute the divergence, see if you get 0. If the divergence is constant 0, then yes, it is surface independent. And if it's not, then it's not. Okay. Let's do an example. Here we go. This is a computational example. This is and I know we just got through spending a bunch of time talking about abstract ideas and reasoning and all this kind of stuff that mathematicians enjoy, right? But to the very important end of having tools that will allow us to solve a problem, right? We've got a computation. We need to know the answer, and the thing that's going to get us the answer is powerful ideas applied strategically. Right. Okay, so here we go. We want to compute a flux. Got a vector field given. We got a annoyingly described surface. It's the part of this that has that other property, blah, blah. But nevertheless, we've got a well-defined question about flux. And let me observe. You could plug and chug this. You could totally plug and chug this. Right? And our surface is a graph. We know how to do the graph parameterization. Our first way that we ever saw for how to compute a surface integral is to pull back through the parameterization, the capital N, all that business, right? You can do that here. It's going to be a little annoying, but you could totally do that here. But look how much easier it's going to be if we use this clever argument instead. And by the way, I easily could have made this example so that the plug and chug was intractable. Right, so don't cling to the idea of I'm a plugger chugger mistake. Right, you definitely are going to need these powerful ideas. Okay, so here's what we're going to do. First thing we're going to do is make sure we understand the surface. Our surface here. It's part of this paraboloid. Okay, great. Let's draw that paraboloid. That paraboloid is, like this, and it extends infinitely downward. That's what a paraboloid is. Now, our actual surface is just part of that paraboloid, not the whole paraboloid. Thankfully, there's way too much surface, right? It's not even bounded. But so just a part of that paraboloid. Which part of that paraboloid? Well, the part that has a z greater than or equal to 0, right? So you have to imagine looking, not at the whole gigantic paraboloid, but just the part that is on or above that blue plane. And I claim what that looks like all together is it's like this. And you can see it has a boundary. Right now, that's just a little bit of geometry. You think about this elliptical paraboloid, kind of upside down. Think about how it gets sliced through by this plane, and what part of green remains. Well, it's just this stuff up here. How we doing? Everybody with me so far? Quick warning. Common mistake I see a lot. Very common mistake I see all the time. It does not include all this business down here. Now, like I say, a lot of students mess this up. I think what happens is students get confused by their own picture. And it's a sympathetic situation to be sure. It is a hard picture to draw, and it's easy to accidentally confuse yourself. You kind of have to draw that purple curve to recognize and acknowledge that that's where the green actual paraboloid surface ends, at least the part that I'm interested in. But when you do that, it makes it look like you're drawing that gray region there that I have crossed out in red. It makes it look like you're drawing that. But if you really analyze the way things are phrased, and you got to interpret the question correctly. And by the way, just to be perfectly clear, that is the responsibility of the student, to interpret the question as phrased, right? And making a misinterpretation of the question will lead you down totally different roads that it all becomes hopeless, and nothing, very often, nothing that's on the page is actually relevant to a true solution to the problem. And it's one of these super dangerous kind of deals, like with symmetry, where you can inadvertently, landmine yourself. So please be careful about this. To be clear, if you look at the phrasing of the question, it says part of the paraboloid. Those points I have X'd out in red are not part of the paraboloid. Right? All this business over here about z being greater than or equal to 0, that's just a clarification of which part of the paraboloid we're talking about. But it is nothing more than that clarification. It remains. S is part of the paraboloid. Right? Does everybody see how that phrasing? Right? There is no ambiguity in how this is phrased. This surface that we are interested in is not closed at the bottom. So make extra sure that you're very clear on what that is. Of course, if you have questions, let's talk about it. Feel free to talk to me after class, of course, also, if that suits you better. But got to make sure that you interpret these right. Okay, so there's our surface. We see its boundary. And let's see here. The question says to compute this flux. And how do we compute a flux? We've got various tools, and again, you could parameterize, et cetera, et cetera. We're going to use surface independence. Now back to here. If you want to use surface independence, you need to establish that your vector field has this property. The way we establish it is with our local test. We take the divergence. We see if we get 0. That's the theorem. Right? Which, by the way, you can see right here. Right here in the diagram. If you want to know if you have surface independence, well, we know from this diagram that divergence being 0 is a test for that. Right there in this little pattern that we've got. Okay. So, off we go. Let's take our vector field. Let's compute the divergence. And sure enough, we get 0. And that means that our vector field is surface independent. That's a huge win. That means we've got all kinds of options for how to rephrase this question. Right? All thanks to one teeny weeny little calculation. How we doing? Everybody see that? All right. So, what to do with this? Let's remind ourselves of what surface independence means. Surface independence means that as long as you don't change the boundary, as long as you keep that boundary fixed, orientation and all, as long as you keep your boundary fixed, if you've been asked to compute a flux through one surface, okay, cool. You've already checked surface independence. You know you can take, you can take any other surface with the same boundary and just compute that one instead. Super flexible. I mean, just a tremendous amount of flexibility we get from this. Pick any other surface. Fix the boundary, of course, very important condition. But any other surface with that same boundary, and go ahead. So that's what we're going to do here. Now we got to again think very carefully about the geometry. I see what my given green surface is. I see what its boundary is. Now I've got to come up with some other surface. The world is our oyster. Take your pick, right? But any other surface that has that same boundary. Now one you could do would be something like that. I don't see how that would be helpful, right? I could also pick some, like a glove. I don't think that would be particularly helpful either, right? The obvious natural choice to actually make our lives easier is to pick that surface there, right? And check it out. That has the exact same boundary, right? The green surface has that purple curve as its boundary. The blue surface, likewise. Same purple curve as its boundary. How we doing? All right. Well, okay. Pretty cool. Now, we do have to worry about orientations. Again, a very big deal. Let's see here. Let's think of orientations. This is oriented downward. And looking at the geometry of this surface, you can see downward would also, I mean, it's tempting to call that inward. A little sloppy, but anyway, it's like that. And now you've got to play the game. You've got to point the thumb in the direction of that normal. Look at the fingers of your right hand. Notice which way the swirl goes. Notice which way the swirl goes. Now think about how that swirl sideswipes against the boundary as it approaches the boundary, and it sideswipes that way. And it's hard to draw the picture here, right? This is, artistically a little bit challenging, so it's helpful to visualize and think about the actual thing, and you got some of this you just kind of have to see in your head. The picture is helpful, I hope. But anyway, that's the induced orientation on the boundary. Everybody buy it? Okay, so next question. That was the orientation we were given on our original surface. That means this is the orientation that we need on the boundary. And so when I ask the question now, okay, looking at my new surface, here's my new surface, which of the two possible orientations, let me do this a little bit different. Looking at, come on, it keeps doing which of the two possible orientations on this surface gives me the correct, needed, same orientation on the boundary? And let's just kind of play the game. What about, let's just, give it the old college try with orange here. If I were to orient the blue surface that way, question mark, right, just hypothetical. Well, thumb, fingers of the right hand, swirl would then go that way, which would orient my boundary that way, which is wrong. That doesn't give me the same orientation that the original surface did. Yeah? Everybody on board? Okay, well, so let's try the other one. Process of elimination, we know the other one kind of has to work, but still, let's think it through. If I orient downward, thumb, fingers of the right hand defines a swirl more kind of like this, which sideswipes like that, which is correct. So, the orientation that I need to make S2 and S give the same boundary orientation, and again, you gotta preserve the boundary orientation and all. I have to orient my new surface downward. And I want to point out, notice this is an unavoidably geometric game, right? There is no sort of quick algebraic workaround. Students are very often tempted to say, the key word was downward, so the first one was downward, so the second one was downward, and it's always no, it isn't. There are weird, strange, various little oddball scenarios where it's not what you would necessarily think, right? So make sure to think it through. And it really does matter. It's again, a big deal. This is a sophisticated idea, and it's therefore worth points. And so you gotta be really careful. Okay. Alright. Well, that's all over but the shouting at this point. We started with the need to compute this, green flux. And then we said, phooey on that, we're gonna compute this blue flux instead because of surface independence, which is awesome. Right? And now, this is pretty straightforward. I can just kind of abandon that whole green surface. It served its purpose. I don't need it anymore. We're just going to look at the blue surface. Right? And the calculation becomes so much easier. For one thing, the normal vector is really easy to write down. Let's see. Secondly, that means that when I look at color choices. Okay, so when I look at the vector field, that's a really easy dot product to compute. This dot product is just minus xy. And this integral, keeping in mind that integral is computed on that kind of solid ellipse in the xy plane, zero by symmetry. Couple of very easy little calculations along the way of using a sophisticated and powerful tool, and presto, no fuss, no muss, right? This is an easy calculation that would have been inconvenient at best had we done this the old-fashioned way. This is a very slick tool. How we doing? Is everybody all right? Okay. All righty, moving along. So now this whole page here is really just kind of a doff of the cap to the diagram. We've got these diagrams which I wrote sort of compactly here, but and there's some patterns to notice that I recognize here, and I just think it's easier to walk through it looking at the actual fuller diagram, which I'll remind you is on the class website. In the let's see, what's it called? Class materials folder in the class website, and it's called diagram.pdf, and it's right there for you to download. This is one of the two big patterns right here. This applies in either place, right? And any vector field that has any one of these properties also has the other two. Regularity issues aside, you got to worry about singularities. That messes everything up. You got to worry about differentiability questions. That messes everything up. But most of the time, when everything works out, this works. Part of which you will notice is the lifetime theorems. So look at what these say right here. This says that if you're looking at a curl, then divergence is zero. That is just a way of saying that when you take two steps, you always get zero. That's one of our lifetime theorems. And vice versa. Anything with divergence zero is also a curl. That means the other version of the lifetime theorem. Like so. So pretty handy. Pretty neato. And then don't forget the other pattern that we've talked about. When you apply the relevant operator, when you take the appropriate boundary, computing on either side gives the same result. And again, this pattern holds wherever in the diagram. So make sure to understand these patterns. They're just off the charts useful. Helps you keep everything organized in your mind. Let's face it. The ideas that we're talking about here are very challenging. This is hard stuff. There's so many pictures and ways of thinking about it, parallel and perpendicular and rotating and expanding, and oh my gosh, there's so much going on geometrically. This will keep it all organized for you. So I cannot emphasize enough. I think this is super, super valuable. Okay. And with that said, we're going to move along now, and we're going to do some computations, and it's just basically just more examples. So, when you find yourself faced with a computation on an exam, such as exam 3, coming up super soon, by the way, right? And the final exam, which is like a few days after that, I can't believe how close we are to the end of the semester, right? So when you fairly soon find yourself faced with, hey, I need to compute either a line integral or a surface integral, right? Vector line integral, vector surface integral. What's the process? How should you approach this, right? What's the organized, methodical, efficient way to get right at the answer? And I really am a big believer. Use the diagram. Let the diagram be your guide. It will basically tell you what to do. It will tell you what has absolutely no chance of working, right? And it will keep you on track. So let it. My advice. And so here's basically the idea. Identify where you are on the diagram. Do what the diagram tells you, infer appropriately, and very often that will tell you exactly what to do. And then, by the way, yeah, always keep your, head on a swivel. Always look for these possible. Every so often you get to use a symmetry argument. Don't let those opportunities go missed, right? Those are awesome. So look for geometric convenience, kind of always. Look for symmetry opportunities. Being very careful not to try to make an odd symmetry argument with a vector line integral, because there is no such theorem, and do not try to make an odd symmetry argument with a vector surface integral either. Neither of those can you use symmetry arguments. But resulting scalar integrals, like we saw here, right? We turned a vector surface integral ultimately into a scalar surface integral, and that scalar surface integral, yes, we can make a symmetry argument. By the way, make sure you're clear in your mind what that symmetry argument is. What plane am I arguing here? Or planes? Maybe there's a couple of options, right? Think through what are the various different ways you could make a symmetry argument there. And do keep in mind on an exam you have to say which plane you're making your argument through. Okay. All right. So moving along, let's do one. This example here, we got a vector field, we got a parametrized curve, looks like, and the question says compute a vector line integral. So two observations we have to make to identify our context, right? And keep in mind, step one is to identify your context. Notice 3 coordinates. This is a 3-dimensional question, right? The curve is clearly in R3. Our vector field has 3 coordinates. Our vector field is in 3 dimensions. So when you're thinking about our context, don't make the mistake in this case of making 2-dimensional diagram arguments, right? The 2-dimensional curl, got nothing to do with this question, right? Green's theorem, off the table. There's no way that Green's theorem is going to help us here, because Green's theorem happens in 2 dimensions, and we are not in 2 dimensions, so there is no Green's theorem, right? So that's the first thing. Make sure to know which world you're living in, and we are in 3 dimensions, and so here we are. And then secondly, again, says we're supposed to compute a vector line integral. Okay, so in the 3-dimensional context, here's a vector line integral. That's what we're looking at. That's our context. Everybody clear on how we find where we are on the diagram? Okay. We've got a vector field, given. We've got a curve, given. I claim the diagram tells us what to do. The diagram is basically screaming at us here, saying, hey, when you have a vector field at that point, compute the curl. Because it's right there. That's the only operator in this diagram that is being applied to vector fields that are integrands of vector line integrals. Diagram says compute the curl, so compute the curl. That's going to be a good first thing to do. It also, by the way, says, hey, this curve that is your domain for this vector line integral, that curve is at that stage. Think about the boundary. Think about what are the points that are the boundary of this curve. In other words, where does this curve start? Where does this curve end? Might be useful information. So we're going to do that too. Okay, and so proceeding, let's compute this curl. And remember, the curl is, del cross, and you got to remember how cross product works. My little hack, by the way, for these computations is I like to just imagine. I don't even write this down most of the time, but I just imagine the little matrix. There's I, J, K, and you remember that you're taking a determinant of this sort of 3x3 symbolic matrix. But in my mind, I just kind of remember that these operators go there, and then I play the usual game in my mind. and I take the y partial of that, subtract the z partial of that, and etc. Right, and you go on down the line. So in doing this, the curl of that vector field, you go through, you play the game. Let's see, the y partial. Okay, so I'm going to have 1 minus, and now I got to subtract the z partial of the second coordinate. That's also 1. Okay. Next, I've got to compute the z partial of that, which is 2x, minus the x partial of that, which is 2x, etc., etc. This is just a computation. Lastly, the x partial of that, which is 2y, minus, and then the y partial of this, which is 2y. And sure enough, 0. So that's an eyebrow raiser of a result. But again, we followed the instructions, we computed the curl because the diagram told us to, and now we get to decide, hey, what does it do for me? What do I get out of observing that the curl is 0? And back to the diagram, what it tells me, because the curl is 0, that tells me that there is an anti-gradient. This vector field is a gradient of something. It also tells me it's path independent, right? But it also tells me that it's a gradient. And so it's worth my time to consider finding an anti-gradient because I know it exists. And by the way, once I find an anti-gradient, that means I can use the fundamental theorem of line integrals. So just simply identifying where we are in the diagram, doing what the diagram tells us to do, has led us to a very desirable way to solve this problem. The diagram is telling us to use the fundamental theorem of line integrals. Everybody see that? Everybody happy? Okay, let's see here. By the way, let's do the other part. The diagram also said to take our curve and look at the boundary and see what those boundary points are. Let's play that part of the game. Let's see here. Okay, this is just a little bit tedious, but you got to take the starting value of t and plug in, and that tells me r of 0. My starting point is 0, 1, 1. And then I end when t gets to 1, which means r of 1. In this case, my endpoint is, let's see here, what is that? Negative 1, 1, e squared. And this tells me something useful. Actually, this tells me two things that are useful. For one thing, it tells me that my curve, let's see here, yeah, I'll do it like this. My curve here starts and ends at different points. If my curve starts and ends at different points, it can't be closed, which means it can't be a boundary. And so going back over to here, the curve that I have been given, right, the curve that is my domain for this integral, I know that it is not a boundary of a surface. And because it's not a boundary, remember, important asterisk about Stokes' theorem, only applies to boundaries. So the diagram is also telling us, by this simple observation of, hey, see if the curve starts and ends at the same point. Stokes' theorem is off the table. Not going to apply. Are we good? All right. Okay, so yeah, the second thing that this little computation has told us is how to use the fundamental theorem of line integrals. Don't forget what the fundamental theorem of line integrals says. Fundamental theorem of line integrals says that when you're computing such an integral, right, it's going to be f of b minus f of a, and well, that's what we just computed. A is that starting point that we have already computed conveniently. And B is this ending point that we've already computed conveniently. So you find the anti-gradient, you plug in these points, boom, done. And the diagram held our hand the whole way through. Everybody happy? My purpose with these examples, by the way, is to help you with diagnosis, right? To figure out how to solve the problem. I'm not going to plug in the details of the arithmetic. Y'all are good at that, I'm sure. Make sure you're good at that, I'll say. But it's plug and chug at this point. Okay, next example. Again, 3 dimensions. Again, vector line integral. So again, here we are. As instructed, we're going to compute the curl. As instructed, we're going to think about the endpoints. Okay. So let's do it. Okay, so the curl of this vector field, as instructed, take the various partials, and what you're going to notice is that they're all 0. And by the way, it's kind of a quickie observation that you notice the first component has only x's, the second only y's, the third only z's, and all the partials it's always kind of, if you will, diagonal partials. At no point are we going to be taking the y partial of the second entry, right? And so they're sort of all trivial little partial derivative calculations there. So cool, anti-gradient exists. Fundamental theorem of line integrals is on the table, and that's nice. Let's go ahead and document. Let's see. So we got 0. That means we do have an anti-gradient. I can therefore look at these boundary points, and I can compute by way of the fundamental theorem. We got an option, and if you want to run with that option, totally fine. Okay, but let's check out the other possibility. Let's play the same game we did previously. Let's plug in t equals 0 and see what comes out. And r of 0 is, let's see here, 0, comma 1, comma 0. And now we'll plug in t equals 1 to get the endpoint. Happens to be 0 to 1 in both of these examples. Don't count on that, right? It's always different. And let's see here. We get 0, 1. Oh, I computed wrong before. Sorry, this is a 1. But I'm sorry, I blew it. This is e to the power of 0, which is 1. Sorry about that. Got to be careful, right? So minus 1 on my paper. So check it out. Here's the cool thing. What we have here is that the starting point and the ending point are the same point. And if you think about now, let's say just interpret geometrically, what does that mean? It means I start at some point, and then I come around and end at that same point. That means it's a closed curve. That means that it is a boundary of some surface. That means there is an anti-boundary surface, and that means Stokes' curl theorem is on the table too. Right? So you take your pick of whichever one of these you like the best. How we doing? Okay. All right, let's see here. Let me get my glasses here. Yeah. By the way, whichever one of these arguments you use, the answer is going to be 0. Let me point out why. Kind of easiest seen on the diagram. Let's see here. Another way to say, by the way, that the boundary of the curve is starts and ends at the same point. Another way to say that is it has no boundary. Kind of doesn't really start anywhere. It doesn't really end anywhere. I mean, it is, in fact, a kind of a closed loop. Okay, so we've been asked to compute whichever point of view you like. We've been asked to compute one of these line integrals. Whichever theorem you choose to use, if you want to use this theorem, this is what you're going to be computing. And look at this. The vector field that is the integrand of that integral is 0. So you can see right here on the diagram, the way things are set up, given what we've computed, we'll be looking at a flux of 0, which of course is 0. Alternatively, if you like, if you use the fundamental theorem of line integrals, and therefore you're going to be computing this, right? Well, I mean, what does this mean when I say that there is no boundary? What I really mean is that these x of b and x of a, the starting point and the ending point are the same point, and so we are subtracting whatever f of that point is, we're subtracting it from itself. And so again, 0. So both arguments actually work out kind of nicely, and both arguments give you 0. So kind of nice how this one works out. Is everybody on board? Everybody see how I'm making such use out of the diagram? Okay. All right. Next example. This one's a little bit weirder. Again, 3 dimensions. Again, vector line integral, same context. We're going to do the same, take the same advice from the diagram. We're going to compute the curl. And let's see, what do we get here? The curl is, well, okay, I got to play this game here. Minus 1. Let's see here. Minus 1. There's our curl. Right? Didn't get 0. What does the diagram tell me then? We looked at our integrand. We computed the curl. We did not get 0. That means there is no antigradient. That means the fundamental theorem of line integrals is off the table. Don't waste your time. Right? And my advice, by the way, you got to keep in mind, when we're grading exam papers, right, we're looking for evidence of what you understand. We're looking for, right ideas. It's not about the answer at the bottom of the page, right? We're looking for persuasive evidence that you know what you're doing. All else being equal, in a situation like this where there is no antigradient, fundamental theorem has no chance of working, you are best off not even having the fundamental theorem of line integrals written on the page, because it looks like you're following up on a lead that can't work. Right? So that'd be my advice. When this happens, when curl is not 0, steer clear of everything over there. Right? Just don't even put it on the page. Which, by the way, related note, don't compute the divergence. It's got nothing to do with this question at all, right? If you compute the divergence of the given vector field, it looks like you're throwing up the what they call a Hail Mary pass. Gosh, I hope this means something, right? There's 0 chance that divergence is going to be relevant to this computation. Don't put it on the page. It's a bad look, right? And likewise, no triple integrals. Don't want to see the word Gauss anywhere, right? Steer clear of all of this as well, right? 0 chance that it's going to be relevant. This is purely a strategic point, just a test-taking, make your grader happy kind of an observation. Does that all make sense to everybody? Okay, and let's see. Oh, by the way, we're probably out of time now. I've got a minute. Okay, so let's see. What can I do in 1 minute? Yeah. Okay. We don't have time to go anywhere with this. So I'm going to go ahead and draw the line right here. We'll pick up here next time. I'm sure I owe you the minute. See y'all later. Have a good rest of your Wednesday. See you on Friday.